So this time we will start linked list, doubly linked nodes. And linked list takes a completely different approach than array list. So instead of storing elements in a contiguous array, it chains individual nodes together. And we will see how. Each node holds its data plus reference to the previous and next nodes. This structure makes linked list excellent for insertions and deletions, but slower for random access. And we will see how. So now linked list also implements both list and deque interfaces. That's why we can use this one for like list purpose, queue, or stack. So we can use linked list in all three cases. Okay. Now let's understand how our linked list works internally. We can come here, and so here we can create basically one linked list. Okay. So here, if you open this one, you will see, okay, this one is constructor. So here we have these node classes. Okay. And this one implements list, deque, and we also have size like all collections. So that's fine. And if you open this one node, then you will see here next and previous and its value item. Okay. So linked list contains these kind of nodes, like chain of these nodes, and each node will point to the next one and previous one in the chain, and also holds its current value. And basically we have iterator, like every collection implements iterator so that we can use for each loop. We can also iterate. And this descending iterator means we can also iterate in reverse order in linked list. Okay, because now we have our previous reference as well. Okay. So we also have some methods, has next, next, remove kind of things. Then we have clone. Also we have to array. Like we also have this to array in the case of our array list, we have seen in last chapter. So that's fine. Write object, we will see this one, write and read object in our serializable topic. So for now, we can skip this. Split iterator we have seen, or we will see in our iterator chapter. So mostly we will cover. So now, basically our linked list contain like chain of nodes. Okay. And each node has its value, pointer, or we can say reference, pointer to previous node, and pointer to next node. Okay. So our linked list is just a chain of these nodes. Now our linked list, this one, this holds reference. Reference is basically two references. First one head, and that will be your first node in your chain, and tail. And we call tail last node in our chain. Okay, so that's it. And everything else we will reach by using these pointers. So we have to traverse everything. We cannot access, let's say, like randomly or in O1, like we did in array list or arrays. So here we don't have any contiguous blocks of memories. But if we add in front, okay, then that operation will be our O1, right? So adding to front will be O1. I mean, we just add one node and we will make that node head, and we will make its next pointer to our like previous head. So that will be O1, unlike our array list that was ON. Okay, we have to shift those elements. But in case of linked list, we don't have to do those kind of things because every node block is independent. Okay, so no shifting of other elements at all. And also this is not like we have insertion from front and back in O1. If we know the reference of one middle node, then we can also add there in O1. Okay. But to find that reference, we have to traverse, right? So that will be on. Now let's see one comparison between array list and linked list. So about array list and linked list implement list interface, but their internal structures make them suited for different use cases. So for array list, our internal structure is basically array, and for linked list, our internal structure is node instances. Operation get index O1 instant. For linked list, we have this ON. Then add reverse add ends. Okay, that is O1. That's fine. So this one is amortized. If we have to add, then we just have to fill our next array slot. But if our array is full, then we have to do resizing. So this one is amortized. Okay. Now add remove in middle. So ON shifts elements. And this one will be O1 after finding reference. Now memory, this one we have compact, extra for node pointers, best for random access and iteration, queues, frequent, insert, and delete. So finding still takes ON. Linked list insertion is O1 only if we have reference to the node. Finding that position first still requires traversal. Okay. And we have seen how our linked list works. Each element is wrapped in a node containing three parts: the data, a pointer to the previous node, and a pointer to the next node. So this doubly linked structure allows traversal in both directions and enables O1 insertion removal once we are at the right position. So we can create our linked list like this. Okay, empty linked list. We can also create from another collection, existing linked list. We can also initialize our linked list with some data like that, list of. We have seen this one in our array list. So same thing here. Now the most important thing is our linked list implements both list and DQ, right? So this one is one important thing. So we can create using linked list directly. We can also create this one with list. We can create here linked list. We can also create here using DQ. We will see DQ later, but for now you can see string DQ. Now we also have here Q. Okay, but we will get different methods based on these interfaces. And we have seen like in our interfaces topic, why we got those kind of methods, because we point reference to here. Even though we are creating linked list on the right side, but the methods we will get will be from our left side references. Okay. So that's one. So that's one important thing. I mean, for Q, you cannot call, let's say, add last, right? But for DQ, you can do that. We have some differences. DQ dot add. We can also have add last, like that. And for Q, we are getting one suggestion for add, but do we have this? So we don't have this add last for Q. Okay. Even though right side we have linked list object, but we will get reference from like methods from our left side reference. So we have discussed these kind of things in our interfaces chapter. So that's not be a problem. Now we can add here. All right. So we can use our linked list as simple list, simple queue, and DQ. So basically our DQ is double-ended queue. And this one is one interface in which we can remove and add elements at both ends, okay, front and back. So we can print this one, but we can also add here. Let's see this one as well. So we can add this one. We can also add, or we can just access list 2, or we can access get using some index value. That's also fine. And we are getting one suggestion that is get first. So you can also use some methods. But if we have to access, let's say, In this one, what you can use, the call to get always fails as an argument is out of bounds. So yes, we can add, that can be anything. Now we are good, and we can compile this. So you can see. So we have some adding operations, add, we can add direct value. We can also add at any particular index, just like array list. We can also add multiple values or another reference of list. Okay. Accessing by using index. So we will traverse from head, and if our this index is closer to our tail, then we will traverse this one from tail. Okay. And our linked list knows the size of our list, right? So if we try to access some index and that is closer to our head, then our linked list basically iterate from head, otherwise from tail. Now next one is modifying, and we can use this one like set, just like array list, removing by index, by value. So that's fine. Okay. For searching, we also have list.index of, list.contains. So we have very similar methods with array list. Now next one we have smart traversal. Linked list is clever. When accessing by index, it starts from the head if index is in the first half, or from the tail if it in the second half. Now next one we have DQ, double-ended queue, and this is where our linked list is very important. So as a DQ, it provides O1 operations at both ends, perfect for implementing queues and stacks. So let's say we have created this one. Now we can use this for like queue and as well as for stack. And we have like they are particular methods, specific methods we can say. So we can also add to the front, and also we can use offer first. So this will not throw exception. Okay. Like that. We can also add to the back. Now accessing ends, get first, get last, peak first, peak last. And we know the difference between get and peak. Okay. So that's same thing. So now next one we have removing from ends. So remove and return. So our remove method or its types basically remove elements and return those removed elements. So deque.remove first, deque.remove last. Safe versions we have here poll first, poll last. Okay. So same thing here, get first and peak first. So for get, we may get exception, but for peak, we will not get. And these are just for like viewing at ends, not removing. So that's fine. Okay, now let's see difference between throws exception and returns null or false. So add first, we will get, we have this operation add first, and if we don't have that element, then we will get one exception. Okay. And also we can check that. Let's say we don't have to, list dot is empty. Yes, we will get true in this case, but can we get dot get first? Can we use this? And let's also do get less, that's also fine. And we use dot size, note that, dot peak first. Okay. So currently our linked list is empty, and we will get one exception. Not compile time basically. We will get this one from runtime, and that will be no such element exception. And this one is from Java 8, basically this line. We will get same thing from here as well. Okay. And now if we comment this, then If we compile this and if we just run this one, we will get null instead of one exception. So our program can continue to execute, okay, instead of crashing. So we have both varieties in methods, right? Okay, now let's see queue operations. First in, first out. So you can use linked list as a queue. We can add at the back and we can remove from the front. So by default, if you don't put here offer last, then that will be still offer last. Okay. So first we added first, then second, then third. Now if we pick, then we will get first. Okay. And if we poll, then we will get first. And our queue will be like that. After removing this, so we have same easy operations. For stack, we can also use. Also, our linked list provide some specific operations so that we can use like stack-based operations. As previously we had the stack and vector classes. So we have same methods like we had in our stack class. And under the hood, they are still using our like add first, add last operations. You can also see if we copy this and if we just paste here, if you open this one, push, then you can see under the hood, this one still use add first. Okay. So, and if we use here pop, then basically we can stack dot pop, then this one will be our get first under the hood or remove first. Okay. So that's fine. And we will see stack and vector classes in our next chapter. And we'll also discuss why our linked list is better choice over stack and vector. Now we can traverse our linked list in the back direction. We can use iterator, okay, stack.iterator, not this one, but descending iterator, okay. Now while our it.has next, then we can print out something, it.next, like that, okay. So we will get third, second, and first. We can compile this and we can run this one. So you can see we got here first, second, and third. So we used here first, second, and third. And at this point of time, our stack will be like that. So we will start from back. So we will get first, second, and third. Okay. So that's how we can use something. Okay, now we can move forward. Stack and deque operations. Push and pop work on the front. We will know why. Okay, under the hood, they use add first, remove first. So for last in, first out behavior, this is exactly what we want. Now next one is iterating linked list. So let's say we have this one. So if you want forward iteration, then just use for each. If you want reverse iteration, then you can use descending iterator. Okay. And we will discuss this one in our iterator chapter, so that's fine. When to use linked list? We can use when implementing queues or stacks, frequently adding, removing at both ends. Memory isn't a concern, and using list iterator to insert remove while traversing. We can avoid when we need frequent random access by index. We are iterating and reading more than modifying. Memory efficiency matters. So that's fine. Now we have summary part and we can move forward with our stack and vector chapter. Stack and vector, the legacy classes. Stack and vector are Java's original collection classes from JDK 1. So before even our collections framework existed, and they are synchronized. What that means we will see in our concurrency. Basically, if we have to do anything, then we have to acquire lock of that instance. You'll see. So thread safe by default, which sounds good. What if we only have one thread? Then this thing will be overhead. So this can actually hurt performance. Today they are considered legacy classes with better modern alternatives, and we have seen those alternatives, right? Or we will see like DQ, we will see we have seen linked list. So understanding them matters because we will encounter them in older code bases. So first one we have vector. So vector is just resizable array, just like our array list, but this one is synchronized, or we can say synchronized array list. Every method is wrapped with synchronized, meaning only one thread can access it at a time. This makes it thread safe but slower. We can create like that. And if you will see this one, you will see mostly all methods are synchronized, protected. You can see this one. Okay. So we can come here and same methods as array list like add, set, remove. So in size equals to vector dot size. Okay, we can also check is empty. But we have some vector specific methods, legacy methods. We don't use those. Add element, element at, remove element at, remove element, and remove all elements. Those things. Now vector versus array list synchronization. All methods synchronized. So for array list, those are not synchronized, but we have some alternatives. Like for array list, even we can create some synchronized list, like this one, and this one will be from our collections utility class. We will see, okay, like that. Or we can also create this one instead if we want like read heavy operations. They offer better flexibility and performance. Okay, then we have performance, slower, lock overhead. This one is faster. Then we have growth, doubles capacity, grows by 50%. Legacy methods has old APIs. Okay, element add, something like that we have seen here. And we don't have to remember these. Okay. Now recommendation, avoid in new code. This one will be your preferred choice, mostly all of the time. Okay, now next one we have stack, LeFo data structure. So stack extends vector and represents a last in first out collection. So we can think of stack of plates. So we add to the top and remove from the top. Basically, we will be using here vector. Okay. And under the hood, this one, same thing, add element, okay, remove element, add something like that. So size -1, that means from like top, okay. Also, we have synchronized all of them. And we will see what that means. So for now, we can skip. So core stack operations, like we discussed already in our linked list chapter, push, pop, peek, okay. Is empty, that's fine. We can also search. So let's say we have this stack. We added first 10, then 20, then 30. So we will get like something kind of plates stacked on top of each other. So our 30 will be at top, right? And if we want to find out like index for 10, then we will get from top, okay? So that will be our 2. So here we have removed something. Okay, so we did pop here. Now at this point, our stack is this one, 10 and 20. And this one will return index like 1 based. So 2 we will get, okay? If our element is not present, then we will get -1. Search returns distance from top. So unlike index of, which returns zero based index from bottom, search returns one based distance from top. The top element has position one. Again, we don't have to use these kind of methods. We will use this index of. Those are deprecated. We can say in some way. Now stack visualization. Okay, so push this one, we'll get this, push. So we will get. So from this one we have top. Okay, 30 we can pop. So we will remove 30, blast in first out, take, we can see 20. So no change. Common stack use cases, undo redo operations, browser history, so back buttons pops from history stack, then expression evaluation, parsing mathematical expressions, function call stack, balanced parentheses, one popular DSA question. So that's fine. And that you can see here. Okay. Now modern alternatives, both stack and vector are legacy classes. Here's what we use instead. So instead of vector, we can use array list. For single threaded code, for thread safe list, we can use synchronized list. Okay. For concurrent read heavy scenarios, we can use copy on write array list. And this one is like real scenario. Most of the time, we don't add too much. We add something like one time, and we will read most of time, let's say 90 to 95%. So we can use this one. Now, instead of stack, we can use DQ. We'll see this one later. We have same. Also, we have seen this one, right, in our linked list. So stack.push, pick and pop, we have same methods. And under the hood, they will be using like add first, remove first methods. So that's fine. Now expect inheritance. Our stack extends vector. Our array DQ implements DQ. Synchronization, not synchronized. This one, but our stack is synchronized. Now performance lower because of this lock overhead. And this one is faster, but at small level, that does not matter. Okay. Now null elements allowed, not allowed. So we can use array DQ for stacks. Okay. Java documentation itself recommends this one, array DQ over stack. A more complete and consistent set of LIFO stack operations is provided by DQ interface. So which should be used in reference to this class like stack. Now why they still exist? Just for backward compatibility. Okay, millions of lines of code use these classes, so removing them would break existing applications, and Java maintains them but discourages their use in new code. We have quick summary and we can move forward with our next chapter, which is HASAT.